In this lecture about higher order functions, we start with a discussion of the order of data and functions. So non-function data are of order 0, numbers and lists, for example. First order functions are functions with the domain and range of order 0. So we could also call these ordinary, old-fashioned, down-to-earth functions. Second order functions, typical higher order functions, which are functions with domain and range of order 1. So here we have the functions that are able to accept functions as parameter and functions which may return functions as result. And this continues to arbitrary order by a simple generalization. So here a number is of 0 order. The same is the case for a list. This is an example of a first order function because it apparently takes a number as parameter and returns a number. Here we also have a first order function because it takes a number and it returns the n factorial. Flip is a higher order function. It's a second order function. It's not necessarily easy to see in Scheme because we do not have static types, but f is intended to be a function because we can see that f is applied. So f is a function. It is the parameter of flip. And what is the result of flip? Well, it's another function. A function in, a function out. And what's the difference between the function that comes in and the function that comes out? This is the order of the parameters. So the order of the parameters are switched, and hereby the name flip. When we pass a binary function, a function of 2 parameters, through flip, we get a function where we have exchanged the order of the parameters. So let us see how flip works in a practical setting. Here we have the subtraction function. 5 minus 6 is minus 1. But if we flip minus, we also switch the order of the parameters, and therefore we get 6 minus 5, which is 1. Here's another higher order function, negate. It takes a predicate as a parameter and returns a predicate. And the predicate which is returned is the negated predicate of the input. So if p returns true, the result of negate p will return false, and vice versa. So let us see how negate works. Number question mark is a predicate, and it gives false when supplied with a symbol as parameter. So now we will negate number. So is x not a number? Yes, it is true. So flip is an example of a very useful higher order function if the arguments are in wrong order. Negate is another useful example of a higher order function because we can negate the effect of a predicate. We can take another example. Odd. 7 is odd. Now we define even. Is even, we call it, which is the negation of odd. So in this way we define a new function. We don't define is even in terms of a lambda. We define it in terms of an existing function and negate a higher order function. So is even? Is 8 even? Yes, it is. Another very useful higher order function is compose. So it is known from math we can compose two existing functions of a single parameter to a single function. So let us compose the square function with a function that adds 1 to its argument. And if we use this function on 5, well, the first thing that happens is that 5 is incremented by the first function to 6, and then we will apply the square function and we square 6 to 36. Many simple and everyday programming tasks can be programmed by means of higher order function. So let us, as an example, take linear search in a list. And what we are searching for is formulated by means of a predicate. So we search in list for the first element that fulfills the predicate, and this is done by straightforward linear recursion. First we handle the case where the list is empty, and if the list not is empty, we can take the first element out of the list to find out if it fulfills the predicate. If that is true, we stop and return the element that fulfills the predicate, else we recur in this way. So simple everyday recursive programming. It might be tempting, whenever you have the need to do linear search in some given context, to program it case by case, but it is much better programming. It's much better functional programming to use a function like find in list and to formulate the predicate that allows you to find what you're looking for. Let us show an example where we have an association list with hair colors. So Ib has black hair, Per has green hair, and Anne has pink hair. And now we want to find the hair color of Per. And Per has hair color green. The pair returned as a result of find in list. As another example, let us find the first one with pink hair using this predicate, and we see that Anne is the first person in our association list who have pink hair. So this variant of finding list only returns the first element that fulfills a predicate. We can of course also program a function that finds all the element in a list that fulfills a predicate. In reality, that is filter, and we will see it in a moment. Here we have a function that returns a list selector function. So make selector function n. So if we make selector function 1, we return the function that returns the first element of a list, and the first element of a list is numbered 0, so therefore we compensate for this difference between 1-based and 0-based understanding of list. And let us see how it can be used. We can define first, second, and third by producing them as a result of make selector function 1, 2, and 3. So now we can ask for the first element of a list in that way. So that's an alternative to car. It's even more useful when we need the first or the third element of a list, because it is rather inconvenient to use car-cutter combination to obtain it. So you may hope that this addition will add the numbers 1, 2, and 3, but it does not. It causes an error because the add function expects numbers as parameters, and it is given a list. The help is nearby. We can use the higher order function apply, and apply takes a list of arguments, a list of parameters in this way, and hereby we are able to add 1, 2, and 3 to get the result 6. Apply is an existing function in most scheme systems. In fact, it is a function which is a cousin to eval. Eval is the interpreter, and eval makes use of apply whenever there is a need to call functions. Now it is time to take a look at a family of high-order functions, map, filter, and reduce, which are very useful for many practical problems that we encounter. Map applies a function m on each element of a list. So if the input list has length n, the output list will also consist of n elements. So the first element in the output list is m applied on E1. The second element in the output list is m applied on E2, and so on. We don't know about the order of applications of m. So m may start from the rear end. We may produce this as a first element and move backwards. It may even be the case in a sophisticated scheme system that m is applied simultaneously and parallel on all elements in the list, and we get these output values computed in parallel. We don't know about the order. It is simple to define map as a recursive function. Map already exists in most scheme systems, so I define my map in order not to make redefinition. And my map gives the empty list if the input is the empty list, and if the list is not empty, we apply the function f on the first element in the list. So we see it here, and we recur on the tail of the list. So it is simple and straightforward. Promise me that whenever you need a map, when you are solving problems in Scheme, do not program your own map in some specific context. Use the function called map. It's a primitive, and it's similar to my map. So let's take a look at some examples. We may map the even predicate on a list of integers. So we get alternating false and true values. 1 is not even, 2 is even, and so on. Of course, we can use the map, the primitive map, which exists in your scheme system, to get the same result. Let's see another example where we map the square function, which I have programmed here in with a simple lambda expression. I map it on the list of 1, 2, 3, 4, 5, 6, and I get the square numbers out of that. A list in, a list out. We can notice that this variant of map is not memory efficient. It takes stack place because map is not tail recursive. So if we attempt to use map on a very long list, we get a memory penalty during the call of my map. So therefore, in a real scheme system, the map function will be programmed in a memory efficient way, such that we can use it on very long lists. Let us see here that map is quite similar to the function called for each, but for each is primarily useful when we do imperative programming. So if I apply even question mark in a for each, I get nothing out of it. The idea is that I apply my function in order to harvest the effect of side effects. And there are no side effects in functional programming. So in general, for each is not useful when we do functional programming. There may be a few exceptions, but in general, we will need a map. Now it's time to take a look at the second function in the family. It's called filter. When we filter a list, it is filtered with a Boolean function, and we apply the Boolean function f on each element of the list. First, for example, on E1, and if f returns true, we keep this element. If f returns false, we get rid of the element. So filtering a list means that we keep some elements in the list and we delete other elements. So filter is applied on a list of elements, and we get a list of elements out of filter, a potentially shorter list than the input list. Here is a possible definition of the filter function. Again, it is a straightforward recursive function. If we filter the empty list, we get the empty list. Else, if the list is not empty, we can take the predicate on the first element of the list, and if this is true, we keep the element and we filter the rest. If the predicate does not hold, if the predicate is not true on the first element, we delete it, and the only thing that remains is the filtering on the cutter of the list. Again, a straightforward recursive pattern that we need again and again in our everyday scheme functional programming. Don't define it yourself in a context where you need it. Use the existing filter function and supply some suitable Boolean function for filter. By the way, it may be the case that filter does not exist in your scheme system. So in that case, you will need to include a definition of it yourself. So before we proceed, we will show a memory efficient version of filter, which is needed in case we filter very large lists. And this is a tail recursive function which makes use of a helping function. And it takes this extra parameter, which is characteristic for many iterative processings by means of tail recursive functions. So if the predicate holds, we accumulate the result in the last parameter. And when the list is empty, we simply return the last parameter. This result parameter is built in the wrong order, and we compensate for that by reversing the final result. So this is one possible iterative variant of filter, which, as I said, is needed in case we filter very large lists. Now it is time to see some examples of filter. Here we filter the list of 1, 2, 3, 4, 5 for even elements, and we get 2 and 4, the only even numbers in the input list. And we can also filter for the odd elements, get the odd elements, by filtering with the negation of even. The last member in the family is reduction, and the reduction function boils down a list to a single element by means of pairwise composing elements. So here in this example, we take the two first elements, compose them to a value by means of up. So here is a single value, which is composed by the operator again with E3, and so on and so forth. So we are composing pairs of elements until we get the single element by the final operation. So what we have shown here is left reduction. We reduce from the left towards the right. This is reduction in the opposite order. We reduce from the right to the left. So we are able to program two functions, reduce left and reduce right, that perform these patterns of operations. Let's take a look at the definitions of the functions. We start with reduce right because it is the most natural function relative to the way we structure lists. So if the cutter of the list is empty, we return the car. So it is kind of difficult to get started because we cannot start on the empty list. Reduction is not easy to define on empty lists, so we need a list of at least one element, and even better, 2 elements. But if there's only one element, we return the element. If there are 2 or more elements, the composition starts with first taking the first element and making a natural recursive combination of the first element with the reduction of the remaining element in this way. So this was reduce right. Reduce left can be programmed iteratively by means of tail recursion. So the helping function takes again an extra parameter where we accumulate the result, and if the starting point is empty, and the starting point is taken here as the cutter of the original list, then we're done and we return res. Left reduction is in a natural way defined iteratively. So we iterate through the elements, and for each element we encounter, we compose it with the already existing result. So this is a natural iteration from E1 to En. So let us take a look at some examples. It is not possible to do reduction of empty lists. Reduction requires at least list with a single element. So we get an error. If we do left reduction with subtraction, so we do a pairwise subtraction of the element, we get minus 13. If we do a right reduction with subtraction, we get 3. Of course, if we do the similar thing with the addition function instead of the subtraction function, we get the same result for both left and right reduction. Let us solve the problem, the annoying problem, that we cannot reduce the empty list. And the solution is to supply an extra parameter for explicitly giving the value of the reduction in case the list is empty. This is called the init parameter, the second parameter. So if the list is empty, we simply return the init value. Else we can proceed as before. Here we call it accumulation instead of reduction. When we are talking about terminology, another common terminology for reduction and accumulation is folding. So in some functional programming context, we talk about folding instead of reduction and instead of accumulation. So now we can see that we are able to accumulate, the empty list. And we can of course accumulate a non-empty list, just like before. The final function I will discuss here is the zip function. It works as a zipper in your trousers or in your shirt. We can zip two lists to a single list. Here is the idea. Two lists, the first here, the second here, and pairs of elements from the first and the second list are zipped with the zipping function C. It is fairly simple to define as a zip function. Again, it follows a simple recursive pattern. Here we will assume that both lists are of the same length, and if we are done, we return as the bottom of the recursion the empty list. Else, if there are elements in both lists, we zip the car of both lists, and we process the cutters recursively in a straightforward way. So here is an example. We const zip the list of 1, 2, 3 with a list of A, B, C, and we get this list of number simple pairs. Let us observe that this is in fact the same that we get if we map const on 2 lists, 1, 2, 3 and A, B, C. So this was the generalized mapping that could be used on functions that accepts 2 parameters instead of a single parameter. So the observation is that we can use map as a zipper.